Okay, let's do the 2022 paper that's come out today, Applied Maths. Motion, let's have a look at question 1, motion. So one train, so one train takes 40 minutes to travel from A to B. So you need a speed time graph of the motion. So let's have a look at that. Okay, so question 1A. Okay, so we need a speed time graph first of all. So let's have a look at what it's up to. It takes 40 minutes to travel from rest to rest. Okay, so it's driving. Okay, so that's speed, then it's starting at 0 and it's ending at 0 at B here. So it's doing some sort of acceleration, flatlining, and then decelerating. So let's have a look. Takes 40 minutes in total, so this time here is 40 minutes. So it's starting at 0 there, that's 40 minutes to rest at station B. Distance between the stations, so total distance is 20 kilometers, so the area under the curve is 20 kilometers, which is equal to the total distance traveled, SAB. Okay, left the station at 10, so that can be 0 or 10 o'clock. At 10:15, speed of the train is this. At 10:30, it's at 48. So that's 48. Maintains that then, yeah, until brakes are applied. Okay, so it takes 40 minutes in total. So yeah, so that's 40 minutes in total. It leaves the station at 10:15, so it's just providing it a little bit awkward. 10:15 and then 10:30, so after 30 minutes, that's at 30 minutes. So at some stage here at 15 minutes, speed of the train is 32. So we're given that. During the first and second 15-minute intervals, the accelerations were constant. 15-minute intervals. Yeah, okay, well, okay, that's fine. The accelerations are constant, but not necessarily the same, of course. So they might not necessarily be the same slope, and probably are not the same slope. So let's just not assume that they're the same slope. Probably a slower acceleration here and bigger there, but it doesn't matter. We can figure that out. Accelerations were constant. So that's the first 15 minutes. That's the second 15 minutes. 48. Brakes are applied, brought the station to rest. Okay. Speed time graph of the motion. Find the time taken for the first 16 kilometers. Okay. So time for first 16 kilometers. Okay. So that's an interesting one. Okay, so the first one is, okay, so this speed time graph, well, we can figure out, so these are all in minutes, so we can figure out the acceleration there. The acceleration is equal to the change in velocity, which is 32, over the time taken, so it's, which is 15, so that will give it, a bit awkward, but now, of course, it's in terms of kilometers per hour, so that's a quarter. So a quarter of an hour. So let's say 0.25, which would be, so the acceleration. So the acceleration would be equal to 8 by 4, so 12, Is that 208? Okay, let's check that. So no, it's not. So it's 8, so it's 12. 128 kilometers per hour. Okay, so acceleration 128 kilometers per hour. Acceleration 2 is equal to v2 minus v1 over t2 minus t1. So it's the time again will be a quarter of an hour. The change will be 16. So it's 4 times 16, which is 24, 64. So A2 is equal to 64 kilometers per hour squared. Yeah. Okay, so that seems quite high, and presumably it's okay. Yeah, it starts at 32. Yeah, okay. Yeah, okay, that's grand. So, and so the acceleration is less, so that's a bit flatter in the second one. So that would be the only difference you'd make on that. So the time taken for the first 16 kilometers and the deceleration of the train. So this so that's your A1, that's your A2, and let's call that F, the deceleration. Well, so the distance, total distance, will be equal to half the base by the perpendicular height for this. Now we just have to keep them all in hours. So half, so in terms of hours, they're all in kilometers per hour, yeah. So that's half this base, 0.25 by the perpendicular height, which is 32, plus area under this curve, which is, well, actually, let's just, oh yeah, they are different slopes, so we do have to do them separately. So it's this bit will be equal to a quarter. So that bit is a quarter by 32, and then the triangular bit will be equal to half the base by the perpendicular height, which is 16. Okay, now the flat bit, we don't know how long that takes, so we'll have to call that, say, T1, let's say. Okay, so that would be T1 minus 30. So, okay, we have to keep the minus a half because it's in hours. By 48 plus half the base by the perpendicular height of that guy. So perpendicular height is 48, so it's half 40 over 60 minus T1, the base by the perpendicular height, which is 48. Okay, and all of that is now going to be equal to 20. So we happily have only one variable there, which is T1, which is grand. Okay, so D is that. So the time taken for the first 16 kilometers. Well, it travels 20, so the first 16 kilometers could be anywhere there, really. But let's just see. Yeah, we'll be able to find T1 from that, won't we? We should. Okay, so we get that's a 16, a quarter of 16, which is 4, which is nice. A quarter of that, which is 8, is it? Plus 4 plus 2 plus 48 into t1 minus a half plus 24 into this awkward guy 2/3. So the total time is 2/3 of an hour minus t1, all equals 20. Okay, so this guy here is 14. So we get 48 t1 minus 24 plus 16 minus 24 t1 equals 6, yeah? Yeah. Okay, so that is 24 t1. Okay, it seems to be coming out evenly enough, which is hopefully a good sign. Minus, what's that, 8? So is equal to 14. T1 is equal to 7 over 12. So in terms of hours, or in terms of minutes, that would be 5 times that, 35 over 60, yeah? So in other words, that is 35 minutes. Okay, so that's a nice even number, so T1 should be fairly reliable. It's 35 minutes. Okay, 35 minutes. So find the deceleration of the train. Might be the easier one first rather than, okay, so let's see if we can get the deceleration of the train now. We know 35, yeah, I'd say the deceleration of the train would be the easier one to go for first. So let's see, part 3, deceleration of the train F will be equal to the change in velocity over change in time. So it's equal to 48 minus 0 over, what's the change? 5 minutes. But we have to put it in terms of hours. So it's that. So it's equal to 48, what's that, a 12th? Lovely. So 48 by, multiplied by 12. Which is what? 48 multiplied by 12. That seems very, very high. But let's just trust it. Minus 576 kilometers per hour squared. Okay, but I suppose, yeah, I mean, we have that up here as an acceleration. They're really putting the brakes on if that's correct. We might have checked that later, but that's okay for the moment. Find the time taken for the first 16 kilometers. Okay, so we don't know where that time is going to be, but okay, we know the whole lot is 20, so it could be anywhere here, and this is the tricky bit. So, well, let's see actually how much area is in that. Okay, so the area of the deceleration bit, so let's call it area 1, let's call it. Area 1 is equal to half the base, which is 5/60ths of an hour, by the perpendicular height, which is 48. So it's equal to, which is, what's that, 12th, isn't it? Yeah, so that's a half of a 12th by 48. So that area 1 is equal to 2 kilometers. So it's decelerating for 2 kilometers. So what's left out of it? 18. So it's 18 from there on. So, and we're asked for, okay, so we now know that the time here is going to be somewhere here during the constant speed bit. Okay, so so these bits, the first triangles are going to be the same. They're going to be unaffected, that area. So that is this distance here, which is 4, and 8 is 12. So that distance, 12 and 2, where's that coming from? Oh yeah, so that is 14 actually. So there to there is 14 kilometers. And we're asked time taken for the first 16. So at what time do we get 2 kilometers here? So that's all we have to wonder about. So well now, so really we just need the area of this fella. So in other words, T1, or no, we're now going to call this T2 minus 30. So that's that, and then by the height, which is 48, is now equal to 2. That should be okay, shouldn't it? All right, so 48 of, we're now calling it T2, minus, the 30, so that's a half. So just be careful of that. So it's 48 minus 24 is equal to 2 kilometers, yeah? So T2 is equal to 26 over 48, which is equal to T2 is equal to 13 over 24 hours. Okay, so it's about half an hour, which is about 30 minutes, which looks okay, yeah, because that's 35. So about T2 is going to be, well, it's about a half, but just over about 31 minutes. All right, okay, and the deceleration there, so that's fine. Okay, that should be done. Okay, not the easiest, I mean, but I mean the method is straightforward enough, but just a little bit convoluted. Lots of just a lot of arithmetic being chugged out there. Okay, so ball E thrown up vertically, speed 42. E up with speed 42. And then T minus 8. Ball F. Same point, same initial speed, so U is equal to 42. We might be able to do relative motion and just the relative velocity is 0 there. That might come in handy. Find where ball E is after 5 seconds and total distance it's travelled in this time. So ball E, so ignoring ball F, so find where ball E is after 5 seconds. Oh. Plus a half AT squared. So where it is after 5 seconds. So T is 5. Okay, so S is equal to 42, 5 minus G over 2, 25. Okay, so that's 210 minus okay, that's 5, let's say, let's just call that G10. So that's 5 by this guy, so that's 125, yeah? So S is equal to 85, is that? 85 meters high? Oh, yeah, could it be, do we know whether it's gone up or down or falling down? Doesn't, yeah, okay, that's something we have to worry about. The distance it's traveled, yeah, is different to where the ball E is. Okay, that's interesting. Okay, so that could be a catch here. So that is the distance it's traveled, but that's the total distance, and that's not a vector. So the displacement might be different. So it might have gone up and down, and the total distance. So let's just say, okay, V is equal to U plus AT. Let's see at what time the total distance is travelled at that. Find where the ball is. Okay, so let's see what the speed. Okay, when it's at the top here, v is equal to u, or 0. So let's just check that. So that's 42 minus g t equals 0. So say let's call g10 is equal to 42. So t is equal to 4.2 seconds. Yeah, so after 5 seconds, so it's dropping. Okay, so the total distance traveled is correct. But where it is different, because that is displacement. So we need to find where it is to this. So that would be a different, and that's pretty tricky. That's just a slight kind of nuance there. I'm gonna have to watch that. So where the ball is after 5 seconds, total distance is traveled. Okay, so total distance traveled is fine. Where it is after 5 seconds. Okay, so we could say, okay, so prove, right, find where the ball is after 5 seconds, total distance traveled. Okay, so what's the maximum height it reaches? V squared is equal to u squared plus 2as. Okay, so that's equal to 0 at the maximum height. So 2as, so 2gs is equal to minus, of course that'll be negative as well, minus u squared, which is 42 squared. So s is equal to 42 squared divided by 20. Okay, so that's 21. So it's 42 by 2.1. So Fs is equal to 84 plus 4.2. S is equal to 86.2. 86.2. Okay, so that is saying 85, 86.2. Okay, so that doesn't appear correct, but because we seem to think that the height, it reaches maximum height after 4.2. I'll have to check that, but it appears that, okay, it's maximum height. Okay, so the total distance is correct at 85. That's fine. So we just have to prove that we just have to find a displacement. Where it is a different thing. So it'll be closer to the ground than that distance. Now when E and F collide, they will each be traveling at speed. Prove that they'll each be traveling at speed. Okay, where E and F collide. Okay, so S of E is equal to U T minus a half G T squared. S of F is equal to U, and U is the same. T minus 8, is it? Yeah. Minus half G T minus 8 squared. And they're going to be equivalent. Okay, so UT minus a half GT squared is equal to UT minus 8U minus a half G, okay, T squared minus 16 plus 64. Okay, so a lot of cancellation here, thankfully. So these UTs will cancel, and we'll also get a bit of cancellation there on that one. So we'll get 0 equals, I say U minus half GT squared cancelling. Okay, plus 8G minus 32. Oh, no, T, that should be T. Okay, so let's just backtrack there. So 8U, 8G, T, yeah, that cancels. So it's that T. So it's plus 8 GT minus 32G. Okay. So that means that 8GT minus 32G minus 8U is 0. Okay, so the time that this all happens, okay, U is what? 42. So 80T minus 320 minus 1633. Okay, so we're going to get a T. 80T is equal to 656. So T is equal to 8.2 seconds. Okay, so they're going to collide after 8.2 seconds. That, well, E has been up there for 8.2 seconds, right? Which means F would be traveling for a very short amount of time, just 0.2 seconds. So it's probably happening when it's kind of reaching the ground. Okay, so prove they will each be traveling with a speed that. So, okay, let's see. V is equal to U plus AT. So V of E is equal to 42 minus GT, 8.2. Oh, I'm only seeing this now. Oh my God, that is a terrible mistake, an oversight. I have said that T was equal to 8. I see that T is less than 8. It's only less than 8. T is a constant, and I was taking T as T being equal to 8. I was thinking, oh, okay, so that will have to be redo over. But okay, and that's why I was wondering why I would end up with that. Okay, so that needs to be redone later on. Okay.